Hi everybody, this is Mr. Zarzak, and in this screencast I am going to look at how we apply Gauss's law to a charged, non-conducting sphere of uniform density. So, look, it's a charged, non-conducting sphere of uniform density. All right, so this 0.1 meter radius, all right, so I'm just going to mark down some stuff as I go here. So that's the size of this thing. Solid non-conducting sphere has a uniform charge density of rho is equal to 0.03 coulombs per meter cubed. What's the E field at the center of the sphere? What's the E field at radius of 0.05 meters? So the in purple I've got 0.1 meter radius, so this 0.05 is inside or below the surface. And then what is the E field at the surface of the sphere? And then what is the E field at 0.2 meters, so outside the sphere? So we want to know at the surface of the sphere where the radius is 0.1. All right, so just kind of zooming in, I'm just going to mark some stuff on my diagram just to make this my life a little bit easier. So this little radius that I've got on my picture here, that's the 0.05 meters. Okay, and the actual radius of the sphere itself, okay, is, what is it? That's 0.1 meters. I'm going to put that as a capital R simply because that's the physical dimension of the sphere. So whereas we could look at the electric field and how it varies below the surface of the sphere or above the surface of the sphere, those would be variable r's, okay, because anywhere from 0 up to 0.01 would be below the surface. Anything from 0.1 essentially out to infinity would be outside the surface. Those are all values that can vary that we can look at the electric field, whereas the physical dimension of r equals 0.1 meter, that's exactly at the surface of the sphere. Okay, so let's go starting at the center. All right, now, if I had tried to draw a Gaussian surface at the very center of the sphere, it would have a volume of 0, in which case we couldn't contain any charge. And Gauss's law really states is it's the electric field contained within a Gaussian surface. So if we can't fit any charge into an infinitely small surface, that would lead us to believe that the electric field is going to be equal to 0. Now, that's a little abstract in terms of concept. All right, so we're going to show that, or I'm going to show that that's actually the case when we look at what I'm going to call part B, which is the electric field at 0.05 meters. Okay, so let's take a look at that now. To do this, we need to apply Gauss's law. So we're going to start by writing Gauss's law. So electric field, so E dA, all right, is equal to the Q enclosed over epsilon naught, where that Q in is just the charge that's inside our little Gaussian sphere, okay, that we're drawing here. All right, so since it's a Gaussian sphere, the closed surface integral of dA, okay, that's really just the surface area of the sphere. Okay, so that's 4 pi r squared. All right, so it's really just a matter of Q in over epsilon naught, where epsilon naught is just a constant. Okay, remember that's the vacuum permittivity. All right. So the trick is we have to figure out how to deal with how much charge is inside there, and that's where this charge density, this rho, is going to come into play. Okay, so charge density is just whatever charge we have divided by whatever volume that we're dealing with. All right, so if we were talking about the entire sphere, all right, it would have some overall fixed value of charge. So I'm going to put that as capital Q, excuse me, okay, divided by V, and I'm going to subscript that V with a capital R to indicate, like, look, if I was talking about the entire sphere of radius capital R, the whole volume contains the whole charge, all right? So that's one tool that I can use, all right? But because the charge density is uniform, all right, well, every little part of the sphere has the same charge density. All right, like if I cut the sphere in half, both halves would have the same rho value. If I cut the sphere into as many slices as I wanted to, they would all have the same density. Okay, and that's the key to this. All right, so imagine some volume that was something smaller, like in the problem that we're literally working right now. Okay, so some volume of some radius less than the actual value of the volume. Okay, well then that would only contain part of the charge. There'd only be some part of the charge inside that volume. Okay, and that's the secret. All right, that's really what we need for this problem is that the density is going to be equal to the charge enclosed divided by the volume of our Gaussian sphere. Okay, so I'm going to take and just move over that little volume of our Gaussian sphere, multiply by rho, and set that equal to the Q inside. All right, and that's what I'm going to substitute in over on the other side here with all the stuff that I've got written in red. Okay, so this is what I want. All right, so moving down here. Okay, this is all just repeat. Okay, and where that little q in goes, that's where that rho over v, and that's little r over epsilon naught. Okay, so from here, E is equal to 4 pi r squared. Okay, rho is just that charge density that's given above. All right, the volume of a sphere is 4/3 pi r cubed. And this is a little r because we're talking about this Gaussian sphere that we've drawn of this radius 0.05 meters. Really, this expression that we need to do some simplification, but really this expression would give us the electric field anywhere below the surface of the sphere, anywhere from the center out to the surface. Okay, so we can cancel out. So let's see, the 4 goes away, the pi goes away. Over here I have r squared, so I can get rid of that. Okay, so this simplifies down pretty nicely. Okay, I've just got E on the left side, which is what I'm trying to solve for. All right, the electric field. So I've got rho. Okay, I've got an r, and then in the denominator, that 3 got left over, so that's still there, and then epsilon naught. Okay, so this would be my expression for anything from the center of the sphere out to the surface. Now, we're looking for a specific value. Okay, so I'm going to plug in some numbers, but this is an important relationship. And also notice, look, if I tried to use this for part A, where r would be equal to 0 at the very center, all right, I would get this E is equal to rho, which is some number times 0 for the very center of the sphere times 3 times epsilon naught. So any numbers times 0 is just 0. Okay, good. All right, what we derive in part B is an agreement what we intuitively reason through in part A. Okay, as far as solving for this, now we're just plugging in numbers. Oops, let me switch back to red here. Gotta stay consistent with the colors. Okay, so the rho, what was the rho? It was 0.03. All right, the radius that we're interested in here, I can see it peeking on my sphere is 0.05. Okay, over 3 times epsilon naught, which is on the equation sheet, 8.85 times 10 to the negative, what is it, negative 12th. Okay, and we could go through and do the unit analysis, and we would see that the units do come out to newtons per coulomb. Okay, I challenge you to do that. Okay, 5.650 e to the 7th newtons per coulomb. So it's like 56 million newtons per coulomb, which is actually a really big value. But for electric field, we wind up getting really big values. So like technically this is the answer, but I want to have that expression written down for us. I'm going to actually skip on here. So let's call what I have in purple part C. I'm going to skip on to part D. I'm going to do this out of order. You'll see why here in just a second. Okay, like we could actually solve for part C right now, but I want to wait for a second before we do. It says what's the field at r is equal to 0.02 meters. Okay, so then we'd be talking about something out beyond. All right, the outside the surface of the sphere. So we'd have our Gaussian surface. All right, would be this. Pretty good. All right, well, it's not perfect, I have to make it nice. Okay, so that's as good as I'm going to get it for now. Okay, so out here, all right, now outside the sphere, you might remember that it's going to behave like a point charge. Okay, and I know we know the formula for the point charge, but I'm going to derive this with Gauss's law just so you can see it. It's such an easy derivation. Oops, go back where you belong. Oh, now it's off center. No, I have to put it back where it belongs. Okay, there we go. All right, anyways, so starting with Gauss's law, so I get E dA is equal to the Q inside or enclosed over epsilon naught. All right, well, if my Gaussian sphere is larger than the sphere itself, well, that means all of the charge is inside that Gaussian sphere. All right, so since it's the entirety of all the charge, that's a fixed value because the sphere itself has a fixed volume, all right, and it has a uniform charge density. So there's some overall total charge, big Q, inside of it. Okay, now when I evaluate the integral of the dA, that's the Gaussian surface. Okay, so that's the surface area of this big blue sphere that we're working with because we're talking about outside, okay, the physical sphere. All right, so that's our 4 pi little r squared. Okay, so again, we're going to derive a relationship that we can really use for the electric field for anywhere outside the sphere. All right, that's equal to big Q over epsilon naught. Okay, and I can take and just move that 4 pi over r squared over and I get Q over 4 pi epsilon naught r squared. And I snuck the epsilon naught in there just because this is the way we're used to seeing the formula for the electric field around the point charge. Okay, and so we could see that we actually derive the electric field for the point charge from Gauss's law. That's where it comes from. All right, and this would be great. I'd love to plug in some numbers, except I don't know Q, but I do know the charge density. Okay, so if I go back up here and say, look, I don't know Q, but I do know the charge density. Okay, and I also know how big the sphere is. So I can use that same little relationship that I started with before. All right, for charge density is just charge over volume. Okay, except this time I'm going to be using the full, whether it be charge density times the full volume is equal to the total charge, big Q. Okay, and that's kind of the secret. That's what I'm going to plug in so that I can actually solve for this. All right, so all this, come here. Okay, except instead of Q, I'm going to put this in here. Okay, and all these are now known values. So really now it's just a game of plugging and chugging. All right, so let's go ahead and do that. We actually get a little bit of simplification first. Okay, so that's important to say too. So let's see, so that's E is equal to rho, which is the given value. All right, times the radius of, or the volume of this thing. So that's 4/3 times pi. Now this is capital R. This is the actual volume of the entire charged sphere. So 4/3 pi r cubed is my volume over 4 pi epsilon naught r squared. Okay, and I do get to do some canceling. Okay, so the 4 and the pi go away, but that's it. I don't get to do as much canceling. Less canceling. Why is canceling so satisfying? Rho r to the third power over, don't forget that little 3. That didn't get canceled a lot. E naught times r squared. Okay, so that relationship right there, all the values now are known. The rho is known. The size of the sphere is 0.1, and then epsilon naught is just a constant, and the radius is at the 0.2 meters. So it's just plug and chug. So let's go ahead and solve for this. And like, by the way, this is the value, okay, for the electric field anywhere outside the sphere, by the way. So what is it? We have, what is the charge density? It's 0.03. Okay, the radius is 0.1. That's the actual size of the sphere itself, divided by 3 times epsilon naught, which is 8.85 e to the negative 12th. Okay, times r squared, and the r that we're looking for is 0.2 meters squared. Okay, so plug all of that mess into your calculator. All right, and we would get 2.825 e to the 7th newtons per coulomb. All right. Okay. By the way, this has a positive charge density, so the direction of the electric field, okay, for both of these is going to be outward. Okay, so if asked which way is electric field, it's outward. If I look at my two relationships, okay, the last thing it says was what is the electric field at the surface of the sphere? Okay, so now I have two equations, one that shows from the center out to the surface, and then one for the center really out to wherever I want. Okay, so like which one do I use? Okay, the answer is at the surface I can use either. All right, so this is why I skipped what I'm calling part C, which is at the surface, okay, until this point. So this is when R is equal to R. I guess I should have written that the other way. When my variable R happens to be the exact value of the surface. That's really what I wanted to say here. So now look, okay, if I take the blue equation, which is for outside the sphere, all right, what do I get? I get E is equal to rho r to the third power divided by 3 epsilon naught times r to the second power. All right, and look, canceling, isn't that fun? Electric field is equal to rho times big R over 3 epsilon naught, which is that equation. Look, the two equations are in agreement with each other. How cool is that? All right, so now it's just a matter of plugging and chugging to solve for the actual value. And of course, I forgot to do that. So I'll show you the substitution. Okay, and then I'll leave that for you to calculate simply so that we can move on with the video. So the charge density, what was the charge density? Is 0.03. Okay, radius of 0.1. All right, over 3 times 8.85 e to the negative 12. Okay, so then again, this is going to have units of newtons per coulomb. It's going to point outwards. I dare say it's probably going to be somewhere in between these two, but there's only one way to find out. Okay, we have to actually calculate. So like I said, I'll leave that to you because I have one more problem, all right, that I want to show you. All right, so let's go on to that. Okay, which is, hey, look, it's a solid non-conducting sphere, has radius r, a charge q is distributed uniformly throughout. Wait a minute, this is like the same problem, just without numbers. Okay, so I purely just want to talk about this in terms of the equations. Okay, now the rho is not given. All right, that's not to say that just because it's not given, it doesn't mean that we can't use it. It tells us that the charge is distributed uniformly throughout. Okay, so because of that, all right, I still have the case where rho is just equal to this, all of the charge Q, which is given, okay, divided by the total volume of this sphere of radius R, capital R, and I can still use the trick of its uniform density. So any charge inside any Gaussian sphere that we draw of any size radius can be applied, okay, to this, whether we're talking about below the surface or outside the surface, all right? So that's kind of cool. We can use that. All right, so we want to know what's the field at r less than r, so when we're underneath, all right, the surface, and then we want to know what is the field at r greater than r. Okay, so let's go ahead and do our derivations here. All right, so red, I'm just going to call that part A. Part 1 doesn't really matter. Okay, Gauss's law, always write Gauss's law. E dA is equal to the Q inside for epsilon naught. Okay, and notice here, look, this little r that I've got written is at some hypothetical radius underneath the surface. Okay, and we'll do the same trick for r greater than r. Okay, so this is going to be for part B, where my Gaussian sphere, okay, it looks like that. All right, I'm going to dash it because it's not real. It exists in our mind. So, all right, so moving on. Okay, so we're back underneath the surface. All right, so that surface area is just the 4 pi little r squared. Okay, I often see students try to apply, when they do that dA, sometimes they get confused and put volume in there. The A stands for area. Say it, the A stands for area. The A stands for area. Okay, so just remember that. All right, so then we've got this Q inside over epsilon naught. All right, so kind of like we did before, okay, we can play around with that charge density substitution. So like little q over v subscript little sub r, okay, is equal to the charge density. So again, we can play around with charge density times that smaller volume of our Gaussian surface is equal to the q inside. Now you might say, wait, but we don't know the charge densities. That's okay. Just wait, just bear with me. Okay, Zarzak knows what he's doing sometimes. So 4 pi r squared is equal to, let's get the colors right. All right. Go faster, Zarzak. We've seen this already. So no. Okay, you can't see this enough. Take your time. E is equal to 4 pi r squared is equal to rho. All right, so now here's we get to do the canceling. It's just so satisfying. 4/3 pi, okay, times little r cubed over epsilon naught. Okay. All right, so cancel, 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 cancel. All right, E is equal to rho r over 3 epsilon naught. Just say, great, it's the same equation we had before, except we don't know what the charge density is. Oh, no, we're stuck. We can't do anything about it. Yes, we can. All right, because we have this relationship, charge density is equal to capital Q over V times capital R as well. So we get to use those. So rho is equal to Q over VR. And right now, my equation in red has that rho. And I'm like, oh, I don't know what the rho is. Yes, but I know what the Q is. It says a charge Q in the given information is distributed uniformly out. The charge Q is given, so that's a legal variable. All right, and the radius of the Q, of the sphere, I should say, not the cube, okay, is also given. So I can use that, which means I can use this, okay. I'm just going to take and do another substitution. Yes, another substitution. Okay, so rho is equal to capital Q, okay, over VR. So that's my rho. And then what do I have left over? I have R over 3 epsilon naught. Okay, so then I can expand this out. Big Q over 4/3 pi capital R cubed. All right, times R. over 3 epsilon naught. Okay, so a bit messier, I'd say, but it's still nothing that we cannot deal with. All right, we do get to do a little bit of canceling. Not a lot, but at least a little bit. What do we have here? We have, oh, look, 3. Oh, boy, we can get rid of 3. Lucky day. Okay, so E is equal to Q times R over. I've got 4. I've got pi. I see the epsilon naught, and I see the R cubed. All right. Now, if I, this, like I said, it looks kind of messy, but the Q would just be some value. It has some charge, Q, blah, 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 coulombs. 4 pi is 4 pi, epsilon naught is the constants on the equation sheet. Okay, and then the big RQ would be however big the sphere is. Really, the only variable, all right, is the little r, all right? So, like, this is for r less than big R. So we're underneath the surface of this thing. So I'm just going to write this one more time just so we can see, like, all this Q over 4 pi epsilon naught R cubed. That's all just some constant value for whatever the sphere is times R. All right, really, the electric field varies linearly as a function of the radius from the center out to the surface. All right, so that's going to be important to us. All right, so then I'm going to take and do the same kind of tricks, okay, for outside the sphere. So outside the sphere is actually much, much simpler. All right, so at the radius of little r bigger than big R, okay, outside the sphere, this thing's going to behave like a point charge. Okay, but I'm going to derive it with Gauss's law anyways because it's one of the easiest derivations we can do with Gauss's law, which means you got to know how to do it. Okay, because it's probably going to show up in some capacity somewhere on some subpart of some question on the AP test. Okay, so we get this E dA is equal to, if our Gaussian sphere is bigger than the physical sphere, well, then all the charge is inside it. Okay, and so for some sphere of some surface area 4 pi r squared, we get this Q over epsilon naught. And so we just get E is equal to capital Q over 4 pi epsilon naught r squared. Okay. Could we write this in terms of kq over r squared? Yes, we could. Okay, and AP would take that. That's fine. All right, I'm going to keep this relationship. All right, just so we can see. I just want to bring it on a new page, just so that it's not cluttered. Okay, so this is for r greater than r. All right, notice, all right, that for these two equations, okay, just like we saw before, all right, if little r is equal to big R, all right, we are going to get the same equation. Like up here, the blue one would just be electric field is equal to Q over 4 pi epsilon naught big R squared. Okay, that's what we get for that. If we did this for red down here, okay, we would see E is equal to Q over 4 pi epsilon naught R to the third power, okay, times little r, where little r is big R, okay, and we'd see that, we'd cancel this out. This 3 would simplify down to 2. Okay, so the equations are in agreement. All right, with Gauss's law, it's pretty sneaky stuff. So when we do things like that, okay, that's a great little mental check that we can do. Okay, and again, this would just be if little r is equal to r. All right, now one of the things that AP can ask us to do here, okay, it would be to graph the electric field as a function of distance. Okay, so what would these two things look like on a graph? All right. I mentioned earlier that if we're underneath, all right, the surface of the sphere, I need a color. What haven't we done yet? Let's do that one. Okay, the electric field varies linearly with distance. That's like a y equals some number times x function, okay? If I were to look at this expression, okay, well, q is just a constant. It's the charge of the sphere. 4 pi and epsilon naught are all just constants. So it's really just, we're taking that distance from the sphere and taking the inverse and squaring it. So it's an inverse squared function is really what, I guess I should have highlighted that too, since it does get squared. Okay, it's really just an inverse squared function. All right, so that'd be like some number times 1 over x squared if we plotted that on a calculator. So what would that look like? Okay, so then on a graph, so Again, this is they like these kind of questions. Okay, you need to be familiar, okay, with what shapes of different common functions look like, like y equals x or 1 over x squared, that kind of thing. All right, so if we were doing electric field as a function of r, okay, well, kind of the key thing is up to the surface versus beyond the surface. Okay, up to the surface, it would start at 0 and it would follow some linear trend, so some constant positive slope like that. Okay, and that's this function right here. All right, you wouldn't need to write this on the graph, but I just want you to see where it's coming from. It just looks neat. Okay, and then beyond the surface of the sphere, it follows the blue q over 4 pi epsilon on r squared. So it's a 1 over r squared function. So it'd be like a decaying exponential thing. Okay, so like something like that, where at distance infinity it would approach 0. That's where the electric field would shrink to 0. Okay, and I got that extra little line in there. Don't worry, this is it. This is the end of the screencast. Okay, once we put this little function on there, isn't that pretty? Okay, so there you go. Those are some things that we can do with Gauss's law in a charged, non-conducting sphere of uniform density. This is Mr. Zarlik saying thanks for watching, and we'll see you next time.